This is the last part of the lecture. Here we will provide guidelines for initializing the wind turbine simulation and evaluate system performance using small signal and transient stability analyses. First, we must calculate the equilibrium point of the wind turbine. For example, assume the turbine operates in MPPT mode. In this case, the pitch angle is 0 and the turbine is at its optimal speed. To initialize a power system simulation, we first calculate the electrical network equilibrium via the power flow solution. This allows us to determine the active power delivered at the point of common coupling, denoted as pH. Next, we calculate the power extracted from the DC bus by the grid-side converter, denoted as PC. This is done by adding the converter losses to the power pH. In our study, we use a first-order inductive filter as the output filter. Therefore, these losses are equal to the equivalent resistance RC multiplied by the square of the converter current IC. If an LC or LCL filter were used instead, the corresponding filter losses would need to be added. After calculating the power PC, we obtain the values of mechanical power, turbine speed, Q-axis stator current, and wind speed by solving the following system of equations. We find the equilibrium point of the remaining states by equating the time derivative of their differential equations to 0. Here we present the values of all states for a given operating condition.
This figure shows the system eigenvalues at the previous equilibrium point. As can be seen, the system is stable. That is, all eigenvalues have a negative real part. Additionally, several eigenvalues have a damping ratio close to 0.707, which corresponds to the value used in the control designs. On the other hand, the least damped eigenvalue has a damping ratio of approximately 0.1. This eigenvalue is associated with the two-mass mechanical system of the turbine drivetrain. This table shows all the eigenvalues, including their settling time, damping ratio, and natural frequency. Participation factors determine which dynamic states the eigenvalues are associated with. This provides information about the dynamic response of the different system elements. Note that eigenvalues 3 and 4 correspond to the least damped eigenvalue, which has a damping ratio of approximately 0.1. The participation factors confirm that these two eigenvalues are mainly associated with states that model the wind turbine shaft. Reference 5 proposes a supplementary control loop to improve the damping of this oscillation mode. This loop was not included in our study. Here we present the implementation of the wind turbine model and its control systems in Simulink. These blocks can also serve as a guideline for writing the system equations in other software programs, such as Python or MATLAB.
There are several models for generating wind speed signals, which enable simulations with realistic wind speed profiles. Two examples are the Weibull distribution, a stochastic method, and the Mexican hat wavelet, a deterministic method. Another approach is the composite model, which combines constant, ramp, and stochastic terms to generate a wind speed signal. In all these models, the wind speed signal is filtered through a low-pass filter before being used to compute mechanical power. See Section 2 and references 13 and 33 for more information. In our study, we use the Keimal spectrum to generate the wind speed signal. First, we define the desired mean wind speed and turbulence intensity. Then we compute the Keimal spectrum and use the inverse fast Fourier transform to convert the signal from the frequency domain to the time domain. Figure 69 shows two examples of wind speed signals obtained using this method.
Now we will show how the wind turbine operates in different scenarios using simulation tests. In the first test, the turbine operates in MPPT mode. As shown in the first subplot, the wind speed starts at 4 meters per second and increases by 1 meter per second every 20 seconds. The second subplot shows the active power, solid blue line, and reactive power, dashed blue line, delivered by the turbine at the point of common coupling. The green line shows the maximum available mechanical power from the wind. Active power increases as wind speed increases until it reaches the rated turbine power of 0.89 per unit minus turbine power losses. See numerical data in Section 2. As expected, reactive power remains constant at its set point of 0.1 per unit and is decoupled from active power. The third subplot shows the turbine and generator rotor speeds. In this test, the two speeds are nearly identical and increase from the minimum to the rated speed. Note that when the wind speed exceeds the rated value of 11.6 meters per second, the pitch angle controller starts increasing the turbine pitch angle to maintain a speed of 1 per unit. See the pitch angle in the fourth subplot.
This figure shows additional variables from the same test. The first subplot shows the magnitudes of the generator stator voltage, Vs, and the point of common coupling voltage, Vh, represented by solid and dashed lines respectively. As the rotor speed increases, so does the induced voltage at the generator stator terminals. Meanwhile, the voltage at the point of common coupling remains close to 1 per unit during the test. The second subplot shows the magnitudes of the generator stator current, Is, and the grid-side converter AC current, IC. These currents increase as the generated power increases. The third subplot shows the DC bus voltage. For clarity, the DC bus voltage is divided by its rated value. No significant DC voltage variations are observed in this test. Since the turbine operates in MPPT mode, the deloading margin, mdel, is 0 in the fourth subplot. As can be seen, all variables are properly controlled and have a well-damped response.
In the second test, the turbine operates in MPPT mode. This figure presents two scenarios. Scenario 1 has a mean wind speed of 9 meters per second, and Scenario 2 has a mean wind speed of 12 meters per second. Both scenarios have a turbulence intensity of 10%. These scenarios represent relatively low and high wind speed cases and are shown with blue and red lines respectively. All subplots show the same wind turbine variables as in the previous test. In Scenario 1, shown in blue, the wind speed is low. Therefore, the turbine power and turbine speed remain below their rated values, and the pitch angle is kept at 0. The second subplot shows how the turbine is able to follow the maximum available power from the wind. See the green and blue lines. The third subplot shows how the turbine varies its speed to track the optimal operating point. In Scenario 2, shown in red, the pitch angle controller adjusts the pitch angle at high wind speeds to maintain the turbine speed at its rated value. We also see that the turbine power is limited to its rated value when the wind speed exceeds the rated wind speed. This figure shows the voltages and currents during the test. Again, since the turbine operates in MPPT mode, the deloading margin, mdel, is 0 in the fourth subplot. As can be seen, all variables are properly controlled and remain below their rated values at all times.
In the third test, the turbine operates in various control modes requested by the system operator. This test allows evaluating the performance of the deloading methods described in the previous section. Two scenarios are analyzed. Scenario 1 uses the pitch angle control deloading method, and Scenario 2 uses the second extended overspeed control method. These scenarios are represented by blue and red lines respectively, and both consider the low wind speed case from the previous test. Initially, the turbine operates in MPPT mode. After 60 seconds, the turbine switches to delta control with a 10% deloading margin, and then with a 20% margin. After 180 seconds, the turbine switches to balance control, delivering a constant power output of 0.3 per unit. Finally, after 240 seconds, the turbine returns to MPPT mode. As shown in the second subplot, the turbine operates below the maximum available power when a reserve margin is requested and maintains a constant power output regardless of wind speed variations when using balance control between 180 and 240 seconds. The turbine speed is the same for both control methods when operating in MPPT mode. However, during deloaded operation, the extended overspeed control method results in a higher turbine speed. See the third subplot. The fourth subplot shows that the pitch angle amplitude is generally higher when using the pitch angle control method. On the other hand, the extended overspeed control method makes more frequent adjustments to the pitch angle. A deeper analysis of these two methods is necessary to select the most appropriate one, especially if the turbine is going to be used with a grid-forming converter. This subject will be covered in future lectures. This figure shows the voltages and currents during the test. All variables are properly controlled and remain within allowable values.
Note how the control system adjusts the deloading margin mdel between 180 and 240 seconds to maintain a constant power output despite wind speed variations.
The fourth test is identical to the third, except we use the high wind speed case instead of the low wind speed case. Similar conclusions can be drawn from this test. The second subplot shows how turbine output power is reduced according to the requested deloading margin under delta control, and then maintained constant under balance control. Note that there are no significant differences in turbine response when using pitch angle control or extended overspeed control. Compare the blue and red lines. As discussed in the previous section, extended overspeed control effectively behaves as pitch angle control at high wind speeds. This figure shows the voltages and currents during the test. All variables are properly controlled and remain within allowable values.
The final test evaluates the turbine response to a voltage sag at the point of common coupling. This simulates a short circuit fault near the turbine terminals. This figure presents two scenarios. Scenario 1 assumes a constant wind speed of 9 meters per second, and Scenario 2 assumes a constant wind speed of 11.5 meters per second. These scenarios are represented by blue and red lines respectively, and in both of them, the turbine operates in MPPT mode. The second subplot shows how active power, solid line, is reduced to comply with the maximum current limitation of the grid-side converter. Reactive power, dashed line, becomes 0 during the fault because active power is prioritized when converter reference currents are limited. The third subplot shows the turbine and generator rotor speeds for both scenarios. Due to the severity of the fault, the shaft oscillation mode is excited, causing the turbine and generator masses to swing. See the thin and thick lines in the third subplot. Since mechanical power from the wind cannot be fully evacuated to the grid, the turbine speed increases until it reaches its rated speed. At this point, the pitch angle controller increases the pitch angle to maintain the turbine speed at its rated value. See the pitch angle in the fourth subplot. In Scenario 2, since the turbine is already at its rated speed, the controller acts immediately when the fault occurs. See the red lines. In this case, the turbine speed momentarily exceeds the rated turbine speed, but remains below the maximum turbine speed. This figure shows the voltages and currents during the test. The first subplot shows the voltage sag at the point of common coupling. The second subplot shows that the grid-side converter current is limited to 1 per unit during the fault. See the dashed lines. Despite the severe disturbance, the control system maintains the DC bus voltage within acceptable values. See the third subplot.
This lecture provides guidelines for simulating a single wind turbine. Future lectures will cover the next steps required to model more complex systems. Topics will include adding a supplementary control loop to mitigate poorly damped oscillations in the wind turbine drivetrain, modifying the grid-side converter control to enable grid-forming operation, modeling the internal electrical network of wind farms to simulate entire wind power plants, describing plant-level control strategies, and introducing discrete time control design for digital implementation. Here, we provide the list of references cited during this lecture. Most of the content presented has been taken from these references, which can be consulted for further information. Thank you very much, and follow us for more content like this.